So let's look at the sample space for flipping 3 coins. Here are the results. S is the sample space. And we put a bracket here, and we have head, 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 tail, head, tail, head, and we have tail, head, head. Continuing, we have tail, 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 head, tail, head, tail, and finally, we have head, tail, tail. There is our sample space. Now, our question was, what is the probability that x, remember x equals number of heads, okay? X is equal to 0. So we simply go over here and count. How many have no heads in it? And the answer is there's only 1. It's right here. Okay? So we have 1, and we divide by the total number of objects in the sample space. There are 8. So the probability of getting no heads, that is to say all tails, when flipping 3 coins is equal to 1/8. Now, what's helpful for us is to use a frequency chart that charts this for us. Here's 0, 1, 2, and 3. Here's x, our random variable, which is equal to number of heads. And on this axis is the frequency. Now, we simply count them. How many cases do we have no heads? And the answer is there's 1. Okay? So we put a little box, looks like that. How many cases have 1 head? Well, we can count them over here. We've got 1 head here, 1 head here, and 1 head here. So there's 3 of them. So we go up to here. Here's 2, and here's 3. Here's my little box, goes like this, and there's 3 of them there. How many have 2 heads? Again, there's 1 here, 1 here, and 1 here. There's 3 again. So there's 3 there. And how many have all heads? Answer 1. What we have here is our old friend, the frequency diagram. What the neat thing is, we can convert this into a probability distribution. We'll take it, looks like this. Okay? On this axis, we have 0, 1, 2, and 3. X is number of heads, which is, of course, our random variable. On this axis, however, I'm going to put probability. Now, if I have 1, there's 1 here, divided by 8, so this is 1/8. Okay, dot, 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 there's 1/8. Here, there are 3 of them out of 8, so this becomes dot, 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 3/8. And you can already see what's going to happen next. Okay? This is our probability density function. Now, the real important point here is that the area under the curve is equal to the probability. So if I fill this in here, 1/8 of this area is in fact the probability we were interested in. If I add up all the probabilities, I'm going to get this. Probability that, probability x is equal to 0 is equal to 1/8. Probability x is equal to 1, 3/8. Probability x is equal to 2, 3/8. And the probability x is equal to 3 is 1/8. If I add those up, I should get 1. And I do. The probability under the whole distribution is equal to 1 because it covers all of the probability possibilities of the random variable, because random variable x can only take on the values 0, 1, 2, and 3. This link between the probability and the probability density function and the fact that we're going to be looking at the the probability of adding is going to be very important as we take up the critical question of how do we deal with the word or and how do we deal with the word and as we look at probability and probability calculations.